So here we've got our wave that has this solution, and we notice this is exactly the solution that we had before, that we saw last time when we were talking about waves, and these quantities have exactly the same form we had before. We have some wavelength, so some wavelength for the wave, so this physical distance here is lambda, and k is again our wave number, just like we had before, 2 pi over lambda. And omega is related to the period of the wave, which is exactly like we saw before. Omega is the angular frequency, which is 2 pi over the period. And then delta is an arbitrary constant, so we can either have the wave like with the shape over here, we could move it back this way, we could move the whole thing over this way. So by varying delta, we can change the points where we find zeros here. In other words, where is the wave kind of located one way or another. So we can move it back or forward or back or anything like that we wanted to. Okay, so just like the solution we saw last time. What I'd like to do now is to think about, well, what other kinds of solutions could there be to our equation? Well, one thing I want to look at in particular is, let's imagine that we have two different shapes of our, and A was the amplitude, just like we saw before. Let's imagine that we have two different waves that would be solutions. So we might have, say, one solution, y1, that's a function of x and t, that's equal to, say, a1 sine k1x, minus omega 1 t plus delta 1. So we've got one solution of our wave equation, we'll call it y1, where we've got this set of constants in there. And then maybe there's another solution, y2 of x and t, which is a2 sine k2x minus omega 2t plus delta 2. So this other solution could have a different wave number, different angular frequency, different phase shift, delta 2, different amplitude, whatever. But we want to assume that both of these are solutions of our original wave equation, the equation that describes the wave. In other words, remember that was d squared, not d squared y, x I mean, sorry. D squared y dx squared is equal to 1 over v squared d squared y dt squared. Now I want to assume that both of these have the same velocity. So let's assume that they both move through the medium with the same velocity. So we've got this relationship between k1, omega 1, k2, omega 2 are related to the same velocity. But this one is a solution to this. So d squared y1 dx squared is equal to 1 over v squared d squared y1 dt squared. But this is also a solution. So we also know that d squared y2 dx squared is equal to 1 over v squared d squared y2 dt squared. So they are both possible solutions to our wave equation, d squared y dx squared equals 1 over v squared d squared y dt squared. They're both solutions to our wave equation. What about the sum? What happens if we add these together? Is that also a solution? Well, let's take a look. So letting a new value for y, call it y3, equal to the sum of y1 and y2, what happens when we stick y3 into the wave equation? Well, dy3 dx, differentiating, well, the sum, the derivative of a sum is just the sum of the derivatives, so we'll have dy1 dx plus dy2 dx. Differentiating again with respect to x, again differentiating each term, d squared y1 dx squared plus d squared y2 dx squared. And then what do we get when we differentiate with respect to t? We'll have dy3 dt will be dy1 dt plus dy2 dt. Second derivative, d squared y3 dt squared will be d squared y1 dt squared plus d squared y2 dt squared. And what we want to know is, does this, the second derivative of y3 with respect to x squared, does that equal 1 over v squared times this? In other words, does this equal 1 over v squared times d squared y1 dx squared plus 1 over v squared d squared y2 dx squared. Well, does this equal that? Well, we know that this term equals this term. How do we know that? Because we assumed that y1 was already a solution to the wave equation. And we know that d squared y2 dx squared is equal to 1 over v squared d squared y2 dt squared. Whoops, sorry. These are all t derivatives, right? Sorry, t squared. Keep that back in black. T, there we go. Sorry about that. Now we know that those terms are equal. So what do we know? We know then that d squared y3 dx squared is equal to 1 over v squared d squared y3 dt squared, so that y3 is also a solution to the wave equation. This is a very, very interesting result. If we have two different solutions, we can find another solution, or we know that another solution is, we can just add these together. We can add them together just very, very simply, add the y values, for the same value of x and the same value of t, just add whatever y values we have, and we know that that's going to also be a solution. Oh, well, this is very, very interesting. Let's take a look at how some different solutions can combine together. Let's imagine at some instant of t, I've graphed these y1 and y2 for different values of x, but let's assume that this is what y1 looks like at some specific value of t. This is what y2 looks like for some specific value of t. So at the same time, this is what they look like. And let's imagine that they are both occurring in the wave, in the medium. So what happens if we have both of them? All we have to do is add them together. And what do we get? This plus this equals what? Well, let's graph. What's the sum going to look like? In other words, what would y3 look like? Well, all we have to do is add them together. So we've got, at this point, y1 is 0, y2 is 0. So what do we get? We get 0. Now, I've tried to draw them with the same wavelength. Let's assume they have the same wavelength. Again, we've got 0 here plus 0 here, so we expect to have 0 here. But what about in the middle? Well, we've got some big amplitude here, some amplitude here, and here in the middle, we'll have whatever the sum of those two amplitudes are. If this is A and this is A, we'll have 2A, an amplitude here. And then again over here, this will be 0, 0, 0. Here we'll have negative A, added together we'll have negative 2A. So we end up with something like that. And obviously you can kind of see what we end up with. That's pretty crooked, but I think you get the idea. What we end up with is a wave that is bigger than these, basically just the sum. If this is some amplitude A, we end up with 2A. Minus A, minus A, minus 2A. We end up with a wave with twice the amplitude. When we have waves that combine together like this to give us a bigger wave, we call this constructive interference. Interference is a term that we use when we have waves that are combining together. Usually we think of interference, or to interfere with something, with kind of a negative context. You know, you could interfere with someone doing something, and if you tried to stop them doing it, or you did something to stop them doing it. So we kind of think of that negatively, so to speak. But with waves, interference is a totally arbitrary, not necessarily good or bad in terms of waves, not necessarily a positive thing or negative thing. It's totally, you get the idea. So these construct, the interference, when we combine these, is constructive. Now the constructive means that they are combining together, giving us something bigger. So this is constructive interference. What if we have maybe something a little bit different than this? What if we have this sort of situation and we are adding these together? What are we going to end up with? Well, here we have 0 plus 0 gives us 0 again. And 0 plus 0 gives us 0 again. Again, I've tried to draw these with the same wavelength. But here we have a positive amplitude. Let's imagine they have the same amplitude. So this is A plus negative A. Well, that's going to be 0. And any point in here, whatever the positive value is up here, seems to be matched by a negative value up here. This thing plus this is just going to give us 0 everywhere. And then likewise, negative here, positive here, that's going to give us 0. Just the whole thing gives us 0. They completely cancel each other out. Now, keep in mind, this could be just for one specific time. At another time, maybe they aren't aligned like this. But just for this specific time, they cancel each other out. This is what we call, well, you can kind of guess if that was constructive interference. This is destructive interference. So when waves cancel each other out, we'll call that destructive interference. Okay, great. Well, what if we have something maybe a little bit more general? Let's imagine we've got two waves approaching each other and see what sort of effect that might have. Let's imagine that over here we've got a wave that is moving to the right, while over here we've got another wave that is moving to the left. What's going to happen when they come together and overlap? And we're going to think about this as at not just one particular time, but what's going to happen over several times, or a number of different times. Well, let's think about this. These two will come together, and let's imagine they're coming at the same, same speed, opposite directions, so negative velocities. So this comes together. These 2 points will come together right in the middle, and we know that 0 plus 0 will give us 0 when those two leading edges get there. But then what happens when these 2 points come together? Well, then it's going to give us twice the amplitude. And then back to 0 when these 2 points come together, this one and this one. And then when these 2 points come together, it will give us a negative amplitude, a negative value, twice the amplitude, negative 2a. So what's this point going to do? It's going to oscillate up and down with twice the amplitude of these two, assuming these have equal amplitude. Well, okay, that's very interesting, but let's think about another point. What about when this point reaches this point? Now, where's that midpoint going to be? Well, maybe somewhere, say, over here. Just try and estimate where are these going to come together. Right here, maybe. Well, when this point comes to this point, that's 0 and 0, so they will give us 0. And then slightly later, this point and this point will come together. And if they are equal distances behind here, they'll come together at the same point. But we've got a positive A and a negative, positive A over here, negative A over here. They will still cancel out. And then 0 and 0, they will come together and give us 0. So this point is not going to oscillate at all. It turns out that as these two waves come together, they will always cancel each other out at this point. And so that point is never going to move. Likewise, if we consider this point and this point, which will come together a little bit over on this side, those will positive, so 0 and 0, negative and positive, 0 and 0, negative and positive, they will always cancel out. So these 2 points, the wave will never, the medium will never oscillate at that point. Well, what's going to happen? What do we have? Well, this one goes up to twice the amplitude, then it comes back down, and then it oscillates on the other side. And then it goes back up and down, but these 2 points never move. We end up with a very, very different looking kind of wave. It doesn't look like this wave or this wave. These look like waves that are moving. We call these traveling waves. This one and this one. But this wave doesn't look like it's traveling. It's the sum, or the superposition. The superposition means the combination of the 2 waves that doesn't seem to be traveling. It seems to be stationary. It's what we call a standing wave. And I can demonstrate a little bit here. So if if I wiggle one end and make waves travel through, we get traveling waves. But if I, oops, I got a knot in my medium here. But if I just move the wave like this, it just goes up and down and up and down. Now you know that it's actually going around in a circle. It's going in a circle like that. But if you look at just, say, one dimension of it, it looks like it's just going up and down and up and down. And that's what this wave looks like. It doesn't look like it's moving through the x direction. It just looks like it's stationary. What's going to happen at other points? Well, at another point, if we look over here and we figure out, okay, well, what points are going to come together over here, we'll get another point that's giving us constructive interference. But when this one is positive, this one will be negative. And so what happens, this one goes up and down and this up and down and up and down like this, opposite this wave here, but still like a standing wave. And we can kind of visualize that. It'll be a little bit harder. If I get this at just the right frequency. There's something like that. Whoops. It's a little bit hard to do. But I think you get the idea that what's happening when one wave is up, I hope you get the idea. It's falling apart now. Let's try that again. Something like that. Oop. It's not very stable. But I think hopefully you get the idea. That what we have then is something like this that is just oscillating up and down like that. And we could look at another one, and then we're going to have another wave that's going up and down and up and down. And those are what we call, as I said, standing waves. Okay, what I'd like to do is to look at some different properties of standing waves in different media and see what properties standing waves have.